Parker's solar probe was already inside the corona, moving through an atmosphere no human-built object had entered before. There was no bright edge to cross, and no sudden flash marking the moment. The boundary was real, but Parker could recognize it only by measuring the particles and magnetic fields around the spacecraft. That boundary is called the Alfven critical surface. Outside it, the solar wind is moving outwards so quickly that magnetic disturbances can no longer travel back toward the Sun. Inside it, the magnetic field still has enough control to carry a disturbance in either direction. Crossing that surface meant Parker had entered a region still physically connected to the Sun below, rather than merely flying through material that had already escaped. So, touched the Sun was not just a dramatic way to say the probe came very close. It described a change in the kind of environment surrounding the spacecraft. Parker had passed from the outward flowing solar wind into the corona that gives birth to it. And getting there was difficult enough. At its closest approaches, Parker moves faster than any spacecraft ever built, while its heat shield faces sunlight hundreds of times more intense than sunlight at Earth. Behind that shield, its instruments sample charged particles, electric fields and magnetic fields in a place that no telescope can examine in quite the same way. A telescope sees light arriving from many depths along the same line of sight. Parker can encounter the plasma itself. That difference turns a distant image into a local measurement. Instead of trying to reconstruct the corona entirely from its glow, scientists can compare what they see from afar with what the probe records while passing through it. The result is less tidy than the smooth boundaries often drawn around the Sun. Parker did not cross one fixed spherical shell and remain inside. It moved in and out as the edge rose, fell, and folded around the changing magnetic environment. The headline sounded like a stunt about surviving heat and getting close. The scientific achievement was more specific. A robot reached a hostile region that had previously been inferred from a distance and began testing those inferences from within. By the end, you'll understand what Parker measured in the Sun's outer atmosphere, and why those measurements made the corona and solar wind much harder to reduce to the old smooth diagrams. If Parker crossed a real boundary, what did it find once it was inside? If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. When NASA said Parker solar probe had touched the Sun, the words brought a clear image with them. You might see the spacecraft grazing a bright, solid-looking edge, almost as if the Sun had a surface that could be brushed by a passing machine. It's an understandable image. In photographs, the Sun looks like a glowing ball with a sharp outline, and touching something usually means reaching the part you can see. That isn't what NASA meant. The visible layer is called the photosphere, and Parker did not skim across it. NASA's own mission description was narrower. The probe entered the Sun's upper atmosphere, the corona. That atmosphere stretches far beyond the bright disk we see from Earth, becoming thinner and changing as it reaches into space. Parker crossed into that extended region while remaining millions of miles above the visible layer. The headline was not false. It compressed a scientific claim into a few memorable words, and in doing so, it made the event sound more like a record for getting close. Yet closeness alone was never the achievement NASA was describing. Parker had already flown nearer to the Sun than any previous spacecraft. The new claim depended on where it was, what the surrounding particles and magnetic fields were doing, and what its instruments could measure after it entered the corona. The difference changes the whole meaning of the mission. A spacecraft can move closer to the Sun without entering a new physical environment, just as climbing a mountain does not tell you whether you have passed through a cloud. Parker's achievement was not simply that the distance number became smaller. It reached a region where the Sun's atmosphere still behaved differently from the solar wind escaping outward through the solar system. Once the bright surface falls out of the image, the achievement becomes both less dramatic and more exact. Parker did not make contact with a solid edge. It crossed an invisible boundary into the corona and measured the Sun from within that atmosphere. The next task is to understand what changed across that boundary and why those changes were strong enough for NASA to say the probe had gone inside. The boundary NASA used is called the Alfven critical surface. The name sounds like a thin layer you might find on a diagram, but it marks a change in how the solar atmosphere behaves. On one side, the corona remains strongly linked to the Sun through its magnetic field. On the other, the solar wind is moving outward so completely that the nature of that link has changed. Inside this surface, a disturbance in the plasma can still travel back toward the Sun along the magnetic field. The material is flowing outward, yet information can move both ways. A change in one place can still affect a place closer to the Sun, rather like a tug passing along a stretched cord even while the cord itself is being fed through your hands. The plasma there is part of an atmosphere that can still answer back. Beyond the Alfven critical surface, the solar wind has become too fast for those disturbances to work their way upstream. The flow carries the magnetic field and its disturbances outward, away from the Sun. It has not lost every magnetic connection in a simple geometric sense, but its behavior has changed. The wind is no longer responding as part of the same tightly coupled region. Here, inside means reaching the coronal side, where signals can still travel back through the plasma and magnetic field. A photograph cannot show that behavior, and distance alone cannot settle it. The Alfven critical surface also changes shape, rather than waiting in space as a smooth, fixed sphere. Its height can vary, and no camera aboard Parker could record a sharp line sliding over the spacecraft. Scientists had to identify the crossing through measurements of the surrounding plasma, its motion, and the magnetic field. Parker's descent was therefore more than an attempt to fly closer than any earlier spacecraft. It was a direct test of where the connected corona gives way to solar wind that has escaped into outward flow. Before deciding when Parker crossed that boundary, we first need this definition. The probe was inside when the Sun's atmosphere could still send a disturbance back toward its source. The first confirmed crossing appeared in Parker's measurements from April 28, 2021. At that point, the spacecraft was about 18.8 solar radii from the Sun's center. For the first time, scientists could attach a date and a measured distance to the claim that a spacecraft had entered the Sun's atmosphere. Nothing struck the spacecraft, and there was no visible edge outside a window. Parker's instruments recorded the surrounding plasma, the motion of charged particles, and the local magnetic field. Those readings changed in the way scientists expected when the probe crossed the Alfven critical surface. The material around Parker no longer behaved like solar wind that had fully escaped. Magnetic disturbances could still travel back toward the Sun. That difference is how scientists knew Parker was inside. If you had been aboard, the crossing would have passed without a bump or flash, yet the instruments would have shown the spacecraft entering a different physical region. The announcement rested on changes recorded at a known time and place. It wasn't a label added later, because Parker had broken another distance record. The particles and magnetic field supplied the evidence. That distinction gives the date its weight. April 28th was not simply the day Parker came very close to the Sun. It was the day its measurements showed that the probe had moved from escaped solar wind into plasma that remained connected to its source. Scientists could identify the event in the instrument record, then tie it to the probe's measured position. The distance still has a limit. 18.8 solar radii marks one verified crossing, not a permanent edge wrapped around the Sun at exactly that height. A single passage shows that Parker entered the connected corona there and then. It cannot show that every part of the boundary always lies at the same distance, or that the boundary holds one perfect shape around the entire Sun. Parker's achievement was therefore more exact than simply flying closer than any spacecraft before it. The probe entered a specific atmospheric regime and measured that regime from within. We know it crossed because the plasma and magnetic conditions changed, not because anyone could see a surface. A remarkable distance became a confirmed entry through direct evidence, fixed to one date, one location, and one recorded change in the Sun's atmosphere. April 28, 2021, marks a real first entry into the Sun's corona. What it does not give us is a universal wall fixed forever at 18.8 solar radii. The crossing happened at that distance under the conditions Parker encountered. Elsewhere, or at another time, those conditions may begin at a different distance. That follows from how the crossing was identified. Parker did not pass through a visible skin. Its instruments detected a change in the plasma flowing around the spacecraft, and in the way the magnetic field connected that plasma to the Sun. Those measurements placed the probe within the corona because the surrounding material was behaving like part of the Sun's connected atmosphere, not because Parker had reached one permanent height on an invisible ruler. So inside the Sun describes a physical relationship. Parker could move into a region where the magnetic field still controlled the plasma, then leave that region as its path, and the surrounding conditions changed. The probe was not brushing against a crust. It was passing in and out of an atmosphere with structure, folds, and boundaries that do not remain at one fixed distance everywhere. That changes how we should hear every later measurement from Parker. The mission is not simply collecting ever closer views while surviving more heat. Some readings come from within this connected coronal regime, while others come from near its shifting boundary or beyond it. Closeness makes those samples possible, but the smallest distance alone does not tell us what kind of solar environment the instruments were sampling. This distinction also protects the science from becoming a race toward one impressive number. A close approach gains meaning when Parker reaches the conditions where the young solar wind is still tied to the Sun and can be measured before it fully escapes. The valuable event is the brief entry into that regime, with instruments awake and able to record what changed around them. We have not yet dealt with the machine that made this possible. Nothing here explains how Parker endured the light and heat, how its flight path created short chances to enter the corona, or how its shield kept the instruments working during those passes. Those are engineering problems, and they follow directly from the boundary we have just defined. Parker had to reach a narrow, changing region, remain functional long enough to sample it, and then carry those measurements safely away. A strong heat shield seems like the main requirement for sending a spacecraft toward the Sun. Build something that can withstand the heat, point the spacecraft inward, and let the rocket do the rest. Parker's solar probe faced a harder problem before its shield could even be tested. Getting close to the Sun requires losing a great deal of orbital energy. The spacecraft left Earth already moving around the Sun at roughly the same speed as Earth. A rocket could push Parker away from our planet, but it could not cleanly remove enough of that sideways motion to send the probe straight into the corona. Moving inward is not simply a matter of aiming at the bright object in the middle. Parker had to slow its motion around the Sun so that gravity could pull its orbit lower. Venus provided a way to do that in stages. During each carefully arranged flyby, Parker passed the planet at an angle that changed the probe's path and reduced its orbital energy around the Sun. Venus did not stop the spacecraft like a brake. Its gravity bent Parker's route, while the timing and geometry of the encounter left the probe on a tighter solar orbit afterward. Then Parker came around again. Another meeting with Venus removed more energy, drawing the next solar pass closer. Repeated flybys traded time for inward reach, allowing the spacecraft to approach a region that launch energy alone could not reach in one clean move. Each pass depended on the previous one, because the spacecraft and Venus had to arrive at the meeting point together. That makes Parker more than a machine built to tolerate intense heating. Its path was part of the experiment. Before any instrument could sample the corona, engineers had to arrange a long sequence of planetary encounters precise enough to lower the orbit one step at a time. The spacecraft earned its closeness gradually. Solving that route still left a separate problem. Venus could help Parker fall inward, but it could not protect the probe once sunlight became fierce enough to damage its instruments. After orbital mechanics opened the way, the spacecraft still needed to cross that final distance and remain alive. Parker's answer was not to make every part of the spacecraft equally resistant to heat. Its thermal protection system created a narrow shadow, and nearly everything that had to keep working stayed inside it. The shield faced the Sun, while the instruments hid behind it, much as you might step behind a wall to escape direct sunlight. Except here, drifting beyond the edge would not mean discomfort. It could mean losing the spacecraft. On the Sun-facing side, the shield could approach about 2,500 degrees Fahrenheit. roughly 1,370 Celsius. Just behind it, the instruments could remain near room temperature. That striking difference existed across a spacecraft small enough to fit inside a launch vehicle. It tells us that Parker did not survive by becoming one uniformly heat-proof object. One side absorbed the extreme load, so that the protected side did not have to. This made orientation part of the life support system. Parker had to keep the shield aimed toward the sun with enough precision that its sensitive equipment remained inside a tight thermal safe zone. The shadow was narrow, and the spacecraft could not casually roll aside or point wherever it pleased. Its geometry set the rules. Every observation had to be made while the shield continued doing the one job that kept the rest of the probe alive. That changes the way Parker looks in your mind. It was not a machine that could simply endure the sun because engineers had wrapped it in remarkable material. It was a machine tucked behind one carefully placed barrier, borrowing protection from a small patch of shade. The carbon composite shield was impressive, but the arrangement mattered just as much as the material. Heat resistance without exact alignment would not have been enough. And the shield did not make the corona hospitable. It bought Parker a limited chance to measure conditions that would still destroy unprotected equipment. The probe could enter, stay aligned, gather what it could, and leave that closest part of its orbit behind. Even after Venus opened the path and the shield made survival possible, Parker was never free to settle near the sun. It could only pass through quickly, protected by a shadow it could not afford to lose. Parker's solar probe makes its closest measurements while moving faster than any human-made object has moved before. At its nearest approach, it travels about 430,000 miles per hour, roughly 692,000 kilometers per hour, and passes within 3.8 million miles of the sun's surface, or about 6.1 million kilometers. Those figures describe more than a speed record. They describe how the spacecraft has to work. If you could watch from a safe distance, the useful interval would seem less like a visit than a precisely timed crossing. Parker does not arrive near the sun, slow down, and spend weeks watching from one protected spot. Its orbit carries it inward through the region its instruments were built to sample, and then outward again. The useful conditions rush past the spacecraft, while the spacecraft rushes through them. Every close approach is a brief encounter with an environment that cannot become a permanent workplace. That changes the rhythm of the mission. Instruments take measurements as Parker crosses regions of changing heat, particles, magnetic fields, and solar wind. The spacecraft gathers a moving slice of the near-sun environment, with each reading tied to where it was and what surrounded it at that instant. Then, the closest part of the pass is over. Parker continues around its orbit, sends its stored data back when conditions allow, and prepares to do it again. Speed alone does not keep Parker alive. A badly chosen path would still expose the spacecraft to conditions it could not endure, and a lost shadow would still place vulnerable equipment in direct sunlight. The rapid pass works because the orbit, the shield, and the spacecraft's alignment have already reduced the danger to a narrow corridor. Parker can exploit that corridor, but it cannot widen it. So the probe is less like an observatory built beside the sun than a package of instruments carried through a hostile place at immense speed. It gets moments, not residents. Across repeated orbits, those moments accumulate into a record, but each one begins with the same restriction. Enter along the survivable path, keep the shield facing the sun, collect the measurements, and move on. The science comes from crossing the corona without ever pretending it is safe to stay. Taken together, Parker's path looks less like a victory over the sun than a very thin line through danger. Venus removes orbital energy a little at a time, allowing the probe to fall closer. The heat shield protects what sits behind it, as long as the spacecraft holds its alignment with extreme precision. Then the instruments gather what they can during each short pass before Parker moves away again. Every part depends on the others. A shield alone could not create this route, and neither could speed or careful navigation on its own. That changes how we should hear the measurements that follow. Parker's data did not come from a machine resting comfortably near the sun, with plenty of time to check the view. Each reading was taken inside a place that remained hostile to a robot designed for that exact task. Repeated encounters with Venus prepared the route over several years, while the shield kept its protected side in shadow. Parker then had only a short time near the Sun before its orbit carried it outward again. There is no broad lesson here about humans gaining easy access to the Sun. Parker's survival points the other way. Even a robotic probe, built around this single mission, can enter only under strict conditions. It cannot turn freely, linger wherever scientists please, or treat the corona as a region it has mastered. Its achievement comes from accepting those limits and working within them. Parker did not become immune to the environment. It became precise enough to pass through, collect a brief set of measurements, and survive to try again. That narrow access gives the later evidence its weight. That difficulty follows every measurement Parker sends home. Each successful pass added another direct sample from a region that could not be reached casually, and repeated passes slowly turned those short visits into something scientists could compare. The mission had solved the problem of getting instruments into the corona without claiming the place was safe, open, or fully understood. Now the route was proven, and the shielded probe was crossing a boundary that earlier spacecraft had only observed from outside. The next problem lay in the readings themselves. As Parker moved in and out, did the corona end at one stable edge, or did its boundary shift around the spacecraft from one crossing to another? The familiar drawing gives the corona a smooth edge, like a clear shell wrapped around the Sun. Parker's readings broke that image. During a single encounter, the spacecraft crossed the Alfven surface several times. It entered the corona, moved outside into the solar wind, and then passed inside again. Parker had not turned around or begun a second visit. It kept moving along its planned path, while the measured conditions changed from one side of the boundary to the other. A smooth shell at one fixed height should give the spacecraft one clean crossing. Once Parker passed through it, the probe should have remained on the same side unless its route carried it back across. Instead, the edge seems to have risen and dipped across Parker's path. A high part of the corona could reach outward far enough to surround the spacecraft, while a lower part nearby could leave Parker exposed to the solar wind again. The probe was moving through ridges and valleys in the boundary, rather than passing through the even surface shown in simple diagrams. You can think of a coastline seen from far away. At that distance, the dividing line between land and water may look smooth. Up close, it bends around bays, runs past headlands, and shifts with each small change in shape. Parker found that kind of local variation at the edge of the corona. One crossing showed where the boundary met the spacecraft at one point. The next showed that its height had changed farther along the route. That changed the meaning of Parker's arrival. The spacecraft had done more than reach an edge scientists expected to exist. Its measurements showed that the geometric image of that edge had been wrong. The Alfven surface was not simply a round layer waiting at one set distance from the Sun. It had protrusions that reached higher and valleys that stayed lower. Those crossings did not map the entire boundary around the Sun. Parker sampled the surface only where its path met it, so scientists could not use one encounter to draw every ridge and hollow across the globe. Still, the local evidence was clear. The corona's edge had become a physical shape in its own right, and that shape now needed an explanation. NASA described that shape as spiky and wrinkled, with ridges, valleys, and narrow protrusions rising through the region Parker sampled. Those features weren't treated as random bumps in messy data. They pointed back toward the Sun, where magnetic fields rise from the visible surface and spread into the corona above. The surface of the Sun isn't magnetically uniform. Some neighborhoods have field lines arranged in ways that hold nearby plasma in the corona, while others connect more freely with plasma flowing away as solar wind. That structure doesn't remain pressed flat against the surface. It reaches upward, carrying the influence of each magnetic neighborhood into the space Parker was crossing. This gives the ridges and valleys a physical cause. Where magnetic control extends farther from the Sun, the Alfven boundary can bulge outward. Nearby, that control may give way closer to the surface, allowing the boundary to dip inward. Parker was moving through those changing regions, crossing from plasma still tied to the sun into plasma escaping with the wind, then back again as the boundary rose and fell along its path. A coastline is a helpful comparison. Its position isn't set by one clean distance from the center of a continent. Bays sink inward, headlands reach outward, and both reflect the land beneath them. The comparison only goes so far, since Parker was measuring a magnetic frontier in moving plasma, not rock beside water. Still, it captures why one altitude cannot describe the whole edge. The shape above depends in part on the magnetic terrain below. There is a limit to what the measurements can tell us. They support the broader link between surface magnetic structure and the wrinkles Parker encountered, but they don't provide a complete label for every spike or valley. Scientists cannot yet point to each measured feature and identify one exact structure on the surface as its sole cause. The connection is real, while the detailed map remains incomplete. That changes the way we ask where the corona ends. Distance alone is no longer enough. We have to ask which magnetic structures push the boundary higher, which allow it to sag lower, and how those structures change as the sun changes. The edge Parker crossed was a record, written high in the corona, of magnetic conditions rooted far below. That record is always being revised. The magnetic field around Parker changes from place to place, and the sun's level of activity changes with time. Because the Alfven surface follows those conditions, it cannot stay at one fixed height. A crossing distance tells us where Parker entered the corona in that region under those conditions. It does not locate a permanent shell around the entire sun. The reason comes from what the boundary separates. Below the Alfven surface, the magnetic field still holds the surrounding plasma in close communication with the sun. Farther out, the solar wind moves too quickly for disturbances to travel back against it. Change the local field, and you change where that break occurs. A stronger magnetic protrusion can carry the coupled region farther outward, while a neighboring valley can bring the break closer to the surface. Solar activity adds another layer of movement. As magnetic regions form, shift, and fade, the surroundings through which the solar wind escapes also change. The corona's edge, therefore, moves not only across different parts of the sun, but across different conditions in the same broad region. Altitude remains valuable, yet it describes one encounter with a changing frontier rather than a universal address. This is why a single number can be accurate and still be incomplete. If Parker crossed the Alfven surface at a certain distance, that crossing was physically real. The spacecraft entered a region where the plasma and magnetic field behaved differently. Yet another pass, through another magnetic neighborhood, or during another level of solar activity, may meet that change at a different height. Neither measurement cancels the other. Together, they show why the boundary cannot be reduced to one radius. NASA's release supports this dependence on local magnetic conditions and solar activity, though it does not give us a full account of how every rise and dip changes across the solar cycle. That will require many more passes and a wider map of the corona. For now, the sound rule is simple. Parker can cross into the sun's magnetically connected atmosphere at a definite place, while the frontier itself remains mobile. Distance marks the entry. The sun's changing magnetic environment decides where that entry is found. Parker's solar probe did more than reach the corona. It showed that the corona's edge had been drawn the wrong way. The old image suggested something close to a smooth shell around the sun, even if its height changed. Parker's crossings revealed a surface with folds, rises, and local spikes, shifting as the magnetic conditions around it changed. The doorway was one of the discoveries that changes the geometry of the problem. Scientists were not sending Parker through a fixed spherical border so it could study the more important physics on the other side. The border was active, shaped by the same magnetic structures rising from the sun below. Its form carried information about the corona, which meant crossing it was already a measurement of how the sun was built and behaving at that place. Repeated crossings made that change hard to dismiss. Parker could move inward, cross the surface, then find itself outside again without the spacecraft reversing course. Set beside the magnetic ridges linked to structures lower in the solar atmosphere, those entries and exits fit a boundary more like a ragged coastline than a polished globe. Along such a coast, A vessel can pass between sea and sheltered water while still travelling forward. The path is steady, the edge bends around it. There is still a limit to what Parker has established. Its measurements overturned the smooth shell image where the spacecraft sampled the corona, and they gave scientists a stronger way to interpret nearby crossings. They did not produce a finished map of the whole boundary for every region and every phase of solar activity. The surface may keep changing as the sun changes, and future passes can fill in parts that Parker has not yet sampled. Once you let go of the smooth shell, the wind just beyond it looks different too. A clean border invites a simple cartoon. Hot material passes one line and streams away as a steady breeze. A folded, moving border suggests that the newborn solar wind should carry structure from the start, with magnetic patterns that reflect the uneven corona beneath it. Parker had therefore changed the expectation before every mechanism was settled. Near this frontier, we should not expect featureless flow. We should expect a young wind still bearing the shape and motion of the place it came from. And that leaves the next issue close by. What does such a wind actually look like? Getting closer to the sun was supposed to clear things up. Farther out, the solar wind has had time to spread, collide with faster and slower streams, and collect the effects of a long trip through space. Near its source, you might expect Parker to find a younger, cleaner flow before all that mixing had blurred the original pattern. Instead, Parker kept running into switchbacks. They weren't isolated disturbances that appeared once and then vanished from the record. They came again and again, common enough in the young solar wind that scientists could no longer treat them as rare oddities. The closer view had removed distance, but it had not revealed the smooth stream suggested by older diagrams. It revealed repetition. That abundance changed how the observations had to be read. A rare event can sit at the edge of a model as an exception, perhaps caused by some unusual local disturbance. A feature that fills large parts of the close-range record can't be placed so easily to one side. Switchbacks had become part of the wind's basic appearance near the sun, one of the main textures Parker encountered while moving through this young outflow. The surprise was magnetic as much as visual. Parker wasn't finding a featureless breeze with a few random ripples laid across it. The measurements showed a wind repeatedly organized into distinct magnetic structures. Whatever their eventual explanation, their frequency meant the simple image of a pristine solar wind had to go. Young did not mean smooth. Close to the source did not mean stripped of complexity. There is still a firm limit to what abundance alone can tell us. Seeing many switchbacks does not reveal where they began, what formed them, or whether they drive other changes in the wind. They could be signs of broader activity rather than the cause of what happens later. Parker's measurements established their presence far more securely than their origin. The coronal boundary had already turned out to be folded and restless rather than a clean shell. Inside and around that boundary, the wind now showed a matching kind of structure. The surprise was no longer just where the corona ended. It was that the young solar wind itself arrived in Parker's instruments already patterned by recurring magnetic turns. A switchback is a bend in the magnetic field, sharp enough that the field briefly points back the way it came. The field flowing away from the sun folds around, then turns outward again. Parker crosses that fold as it moves past the spacecraft, much as a boat might cross a crease traveling across water. The instrument records a reversal because the magnetic direction truly changes around it. That makes the name more physical. Nothing is switching inside the detector, and Parker isn't confusing one weak signal with another. The spacecraft is passing through a kink carried by the young solar wind. On one side, the field points mainly away from the sun. Inside the kink, it swings through a different direction, sometimes turning almost completely back on itself, before returning to its earlier course. The speed measurements add another part of the structure. As the magnetic field turns, Parker also detects a burst of faster-moving material associated with it. The change in direction and the change in speed arrive together, behaving like parts of the same parcel. It's closer to a quick jet wrapped inside a magnetic bend than to a compass needle twitching for no reason. That connection is why scientists can treat switchbacks as coherent features in the flow. Random instrument noise could produce scattered jumps, but it would not repeatedly line up a field reversal with a matching burst of speed. Parker found the two changing together often enough to reveal distinct packets moving through the wind. Each packet has a recognizable form, even though its edges and strength can vary. So the young solar wind isn't simply a smooth stream with a little static laid over it. It carries organized kinks, and those kinks move with faster parcels of plasma. Parker can measure their direction, speed, and passage as linked behavior. They are real structures in the material leaving the sun. Coherence, however, doesn't tell us how each structure was made. The measurements alone cannot decide whether a given bend began near the solar surface, formed later as magnetic fields shifted, or belongs to one of several processes operating at once. Nor do they yet settle how much switchbacks contribute to heating the corona or pushing the wind faster. Parker has shown us the folds themselves. Their birthplace remains unsettled. It would be easy to treat switchbacks as wrinkles the solar wind picks up with age. The plasma travels for millions of miles, meeting other flows and carrying its magnetic field through a changing environment. Perhaps those sharp bends simply collect along the way, like damage on something that has spent too long in transit. If that were true, Parker should have found a cleaner wind as it moved closer to the sun. It found the opposite. During Parker's early close encounters, switchbacks appeared again and again in the young solar wind. They weren't a rare disturbance hiding between long stretches of smooth flow. The closer measurements made them too frequent and too prominent to dismiss as a minor feature added far downstream. Distance had been softening the view. By the time the solar wind reaches spacecraft near Earth, separate structures have had more time to spread, overlap, and change. A magnetic reversal that began as a sharp fold can look less distinct after that long outward passage. The fast jet of plasma associated with it can also blend into the surrounding flow, leaving a weaker trace of the original event. Parker samples those structures before so much blending has happened. Its instruments pass directly through a reversal, record the magnetic field turning back on itself, and measure the faster parcel of plasma traveling with that turn. Close to the sun, those linked signals remain easier to separate from the background. Proximity doesn't merely give scientists another view of the same wind, it changes what they can recognize inside it. That produces a slightly awkward result. You might expect the wind near its starting point to look simpler, as though Parker had arrived early enough to see the outflow before it became disordered. Instead, the young wind is crowded with repeated bends. Moving inward reveals more structure, not less. This still doesn't tell us what makes a switchback. The close encounters cannot, by themselves, choose among competing ideas about where each fold begins, or whether several processes can produce similar signals. Yet they do narrow the argument. Structures that grow more prominent toward the sun are difficult to explain as mere scars acquired far away. Switchbacks belong near the wind's formative region, and the search for their cause must now move upstream toward the place where that young wind is being made. Parker's measurements leave us with a different sun. The solar wind near its birthplace does not resemble a smooth breeze that slowly picks up a few wrinkles on its way past the planets. Switchbacks appear too often for that. They fill the young wind with sudden turns, making the magnetic field point back toward the sun before swinging outward again. These are not rare flaws around the edges of an otherwise calm stream. They are part of the scene Parker repeatedly found. The changes also have a recognizable shape. During a switchback, the magnetic field turns in a coordinated way, while the surrounding plasma often moves faster. Those two signals belong together. Instead of shapeless turbulence, with every part changing at random, Parker sees structures that hold together as they pass the spacecraft. You can think of them as kinks carried in the flowing plasma, or magnetic snaps that briefly fold the field back against its main direction. That changes the image we should keep in mind. The young solar wind is still streaming away from the sun, but it carries organized bends, pulses, and reversals within that outward motion. A river can travel downhill while forming currents that twist sideways or briefly curl back. In much the same way, The wind's overall direction does not tell you what every small region inside it is doing. Close to the Sun, those local motions are frequent, sharp, and tied to the magnetic field. The old breeze comparison fails because it hides the very behavior Parker went close to the Sun to measure in the first place. Parker has therefore settled one part of the problem. Switchbacks cannot be treated as minor disturbances added to a simple wind. They are common enough and coherent enough to demand a model in which structure is present near the beginning. What Parker has not settled is just as important. The measurements do not yet show whether every switchback forms through the same process, how much energy these structures add to the plasma, or exactly how they affect the wind's acceleration. So the argument now moves to their birthplace. Some switchbacks may begin low in the Sun's atmosphere where magnetic fields meet, separate, and reconnect. Others may take shape as the wind travels outward, or emerge through several processes working together. The breeze has given way to a magnetically busy stream. The unresolved part is where its organized folds are made. Parker's closer passes gave scientists something they hadn't had before, a way to compare switchbacks in the young solar wind with magnetic structure much farther down, near the Sun's visible surface. In 2021, NASA researchers reported that some signatures could be traced towards small regions where magnetic fields spread out from the solar atmosphere. The folds were no longer anonymous shapes found somewhere along Parker's path. At least some carried a connection to the place where the solar wind begins. That changes what an explanation must account for. Before Parker reached this region, scientists could argue that switchbacks formed only after the solar wind had moved well away from the Sun. Plasma traveling outward can develop waves, turbulence, and other changes, so perhaps the folds were late additions to a wind that began without them. The near-surface connection makes that answer too broad. Some switchbacks appear to have roots close to the Sun, before the wind has crossed much of the space between the surface and Parker. You can think of this as locating one end of a trail without seeing every step that made it. Parker can follow a magnetic connection back toward the surface, but that does not reveal every event that shaped the fold along the way. The spacecraft also samples one place at one time, while the Sun sends out different kinds of wind through magnetic regions that keep changing. A switchback tied to one surface structure may not have formed like another switchback measured elsewhere. The result is strong, though narrow. It shows that the Sun itself is involved in making at least one part of the switchback population. It does not show that every fold has the same birthplace, or that a single process produces them all. Some may begin near the surface, others may develop farther out, and some may be altered during both stages. Parker removed one easy escape from the debate. Scientists can't explain every switchback as clutter created late in the outward flow. The remaining problem now sits closer to the Sun. Which magnetic process near the surface can send these folded structures into the young solar wind? One leading answer begins where two kinds of magnetic field meet. Near the edge of a coronal hole, some field lines are open, reaching away from the Sun and carrying plasma into space. Nearby lines are closed, looping back to the solar surface. Those neighboring regions don't always stay separate. A closed loop can meet an open field line and reconnect with it. The lines break and join in a new arrangement, though break is a simple description of what the plasma and magnetic field do together. Energy stored in the old arrangement is released. Hot plasma moves outward, and the newly connected field can leave with a bend already built into it. That bend may become one of the sudden reversals Parker flies through. This family of ideas is called interchange reconnection. It gives us a physical link between magnetic activity near the solar surface and a kink carried into the young solar wind. The switchback doesn't have to appear later because the flowing plasma becomes unstable far from the Sun. It can begin close to the surface and travel outward with the wind itself. Something related may happen along coronal hole boundaries. Magnetic regions on the surface shift and press against each other, shearing the field instead of leaving its shape fixed. That stress can also produce an S-shaped bend that moves away from the Sun with hot plasma. Reconnection and boundary shearing aren't identical processes, but both place the cause in changing magnetic geometry near the source of the wind. This is why the mechanism family carries so much weight. It connects a specific place on the Sun, an interaction between neighbouring fields, and the outward moving reversals Parker measures. The pieces fit without requiring every fold to form by chance during the long trip outward. A strong fit is not a final verdict, though. Competing models remain active, including explanations in which some bends develop or change as the solar wind expands. Parker's readings are helping researchers test how much of the switchback population each process can explain. Interchange reconnection may make some of them, boundary shearing may make others, and later changes may reshape bends that began near the Sun. The debate has moved beyond whether the Sun is involved. It now concerns which magnetic interaction accounts for which switchbacks and how much each process contributes. Parker's solar probe did not end that debate simply by flying closer to the Sun. What it did was make the competing explanations easier to test. Earlier spacecraft met switchbacks only after the solar wind had travelled much farther, giving the structures time to bend, mix, weaken, or be altered by the surrounding flow. Parker sampled them at smaller distances from the Sun, where some of those later changes had less time to blur the signs of how each switchback began. That changed what researchers could ask of an origin model. A theory could no longer explain the readings only in broad terms and leave the place of formation uncertain. If switchbacks formed mainly far from the Sun, their behaviour at Parker's smaller solar distances had to fit that claim. If they were launched by magnetic activity near the solar surface, then they might retain some trace of that beginning as they moved outward. You can see why getting closer did not supply the answer by itself. It reduced the room each explanation had to hide. NASA researchers also looked beyond the number of switchbacks Parker encountered. They studied which way the folds pointed and whether their shape persisted as the spacecraft passed through them. A durable kink moving outward from near the Sun should not always resemble a brief distortion produced within the local flow. Its orientation may relate to the magnetic structure it came from, while its persistence helps researchers judge whether they are seeing a stable feature or something that forms and fades nearby. Neither reading acts as a simple label, but together they place tighter limits on the possible histories. The result is a stricter argument. Models now have to account for where switchbacks appear, how long they remain recognizable, and whether their geometry matches the magnetic organization closer to the solar surface. They must also explain how those traits change as the wind expands. The same Parker dataset can still support more than one mechanism, especially if different switchbacks have different origins. Better readings can narrow a disagreement without closing it. Parker's contribution was to bring the theories nearer to the place where the solar wind begins, then make each one answer to details that distance once concealed. Parker changed the argument by taking away much of its room to wander. Before the probe reached the near-Sun region, a switchback seen farther out could have formed close to the solar surface somewhere along the expanding wind, or through some mixture of both. Parker found that at least part of the population carries a clear connection to magnetic structure near the surface. That doesn't give every switchback a birth certificate, but it does rule out the idea that their origins can be placed almost anywhere with equal freedom. The leading family of explanations now begins with the Sun's tangled magnetic field. One strong candidate is interchange reconnection, which happens when closed magnetic loops meet open field lines that reach into space. The lines break and join in a new arrangement, releasing material and sending a bend outward with the solar wind. Similar activity around the borders of coronal holes may produce related effects. Parker's readings give this family more weight because the patterns appear close to the regions where those magnetic changes can happen. More weight is not the same as a final verdict. NASA's reports on the switchback findings leave room for several origins and for the possibility that different members of the population are made in different ways. Some may carry a bend created near the surface. Others may be changed, strengthened, or even formed as the wind travels outward. A striking shape in the data can tempt us into giving it one cause, especially when that cause fits a clean diagram. The Sun has not agreed to be that cooperative. So Parker's achievement was narrower than solving the switchback mystery, and stronger than simply finding more examples. It located the main battlefield near the solar surface, made magnetic explanations answer to readings from the source region, and reduced the number of stories that can survive without such tests. The uncertainty left behind is part of that achievement. We now know where the hardest origin tests belong, even though no single process has accounted for every case. That leaves a different standard for the next step. A proposed mechanism cannot merely resemble the structures Parker sees, it must do measurable work, adding heat to the solar wind, accelerating its particles, or producing changes that the probe can test under stated conditions. Switchbacks showed where the argument begins. The next evidence has to show what the wind is actually doing there. The simplest image of the solar wind is a blast that finishes its hard work near the Sun. Plasma escapes the lower corona, reaches open space, and then coasts outward like material thrown from an explosion. Its speed can vary from one stream to another, but in this view, the important heating and acceleration have already happened before the wind begins crossing the inner solar system. Parker found something less settled. Its readings showed that at least some streams were still gaining heat and speed after leaving the lower corona. The plasma wasn't merely carrying energy deposited earlier. Energy was still being transferred into it as it expanded and moved away from the Sun. The wind had departed, yet its physical state was still changing. You can see why that changes the problem. A gas that expands freely tends to cool because its particles spread apart and spend energy pushing into a larger volume. If the solar wind stays hotter than that simple expansion permits, some process must keep feeding energy into the particles. If the flow also gains speed, available energy must be turning into outward motion along the way. The source could involve waves, turbulence, magnetic changes, or some combination that behaves differently across different streams. Parker's result alone doesn't settle which pathway dominates, and it doesn't explain every kind of solar wind. It establishes something more basic. The mechanism can remain active where a spacecraft can pass through the plasma and measure the changes directly. This doesn't move the whole acceleration process far from the Sun. Much of the wind's early development still happens low in the corona, where magnetic fields guide escaping plasma and conditions change quickly with height. The correction is narrower. The shift from active heating to passive coasting isn't as early or as clean as the simpler model suggests. Getting close, then, gave Parker more than a better view of the launch region. The probe entered a region where the solar wind was still changing. Particles gained heat and motion as the flow developed around the spacecraft. A firmer test follows one stream over a set time. Its readings link later heat and speed to conditions nearer the Sun. In 2024, researchers found the kind of comparison they needed. Parker's solar probe and solar orbiter had both passed through the same fast stream of solar wind, but at different distances from the Sun. Parker sampled it in the outer corona. Solar orbiter encountered it farther away, near the orbit of Venus. Together, those readings gave researchers two views of one moving flow, separated by a long stretch of its outward flight. That shared identity was the key. Comparing separate streams can be misleading because each one may leave the Sun with different speeds, temperatures, magnetic fields, and particle mixtures. A difference measured later might have been present from the start. Here, the team could connect the plasma seen by Parker with the plasma later measured by Solar Orbiter. You can think of it as placing two instruments along the same stretch of moving water, then watching how the flow changes between them. Distance had become part of the test. The first spacecraft recorded the stream closer to its source, while the second recorded what it had become after traveling outward. If the wind were merely coasting between them, its later condition should follow from expansion alone. The plasma would spread into a larger volume and cool in a fairly predictable way. Added heating or acceleration would mean that energy was still moving through the stream during its flight. This let the researchers examine changes in particle motion alongside the behavior of waves carried through the plasma. They could test whether wave-related energy was being lost as the wind traveled, and whether the particles gained heat and speed across the same interval. Since both spacecraft had sampled the same stream, those changes were harder to dismiss as differences between unrelated parcels that happened to pass each probe. We are looking at one flow at two stations rather than two flows that merely seem alike. It was a rare and valuable arrangement, though its limits are clear. The result followed one named fast wind stream under one set of source conditions. It wasn't a complete map of every solar wind stream, and it didn't settle every question about how the process begins closer to the Sun. It provided a real before and after view across space that let scientists test continued heat and added speed without relying on one reading point. The remaining task was precise. Compare the wave energy that disappeared with the energy the plasma appeared to gain. That comparison gave a clear result. In the fast wind stream studied in 2024, the large Alfven waves carried enough energy to explain the heat and added speed measured between the two spacecraft. They weren't simply magnetic ripples traveling alongside the wind. Their energy was part of what the wind was using as it moved outward. Some of that energy went into heat through wave damping. The fluctuations weakened as the plasma expanded, and the energy they lost didn't simply vanish. It was transferred into the plasma, helping its particles maintain more thermal energy than expansion alone would allow. Without continued heating, the spreading wind should have cooled more sharply. The measured decline in wave energy was large enough to supply the missing heat over that interval. The waves also pushed. Alfven waves carry pressure, and when that pressure changes across distance, it can do mechanical work on the surrounding plasma. In this stream, that outward push helped increase the wind's speed. One share of the changing wave energy warmed the plasma, while another helped drive it away from the Sun. The same measured energy transfer produced both the heat and the added speed. This is what we mean when we say the waves paid the bill. Scientists could estimate how much energy the plasma gained as heat and outward motion. Then compare that amount with the wave energy available to lose. The figures matched closely enough for the mechanism to work without an unseen reserve being added to the account. For this particular fast stream, the waves didn't merely have the right character or appear in the right place. They carried enough energy, and they gave up enough of it, to explain a real physical change. That measured yes still has edges. The study followed one known fast wind stream under set source conditions. It does not show that Alfven wave damping explains every hot part of the corona, every slow stream, or every stage of the wind's escape. Other pathways may carry more of the load elsewhere. Yet, within the interval Parker helped observe, the result is hard to dismiss. The magnetic structure was not background decoration. Parker caught Alfven waves giving energy to the plasma and pushing the flow outward. The transfer was strong enough to produce the measured heat and added speed. This is the advance Parker solar probe made possible. A long-standing candidate was caught doing enough work to account for both heating and acceleration in a fast stream beyond the outer corona. The claim is narrow because it belongs to that stream during that interval under those source conditions. Within those limits, though, the answer is firm. Alfven waves were transferring energy into the plasma, and the measured transfer was large enough to explain the measured change. That turns an old possibility into something scientists can test more sharply. Before Parker reached this region, wave heating had strong physics behind it, along with years of indirect evidence. What had been missing was a close reading that could follow the energy itself, how much the waves carried, how much they lost, and whether the plasma gained enough to match. In this case, those parts met. The energy budget closed well enough for the proposed pathway to move from plausible to demonstrated. It still isn't a universal answer to coronal heating. It doesn't show that every part of the corona is heated in the same way, or that every solar wind stream receives the same share of its energy from Alfven waves. It also doesn't erase other mechanisms that may dominate in other places. Solar plasma can be heated and pushed by several processes, and their relative importance may change with magnetic structure, source region, distance, and the kind of wind Parker enters. There is another limit worth keeping clear. Finding continued heating beyond the outer corona doesn't make the lower corona less important. The plasma had already been heated and accelerated before Parker sampled this later transfer. What the spacecraft measured was an extension of that process, Energy was still being converted after the wind had begun its outward flight. The story didn't start there, but it also hadn't finished. So the mystery has become smaller and more precise. We no longer have to ask whether Alfven waves can ever provide a measured share of the heating and acceleration. Parker showed that they can in at least one fast wind stream. Now the pressure falls on the categories themselves. A fast stream can carry this clear wave-driven sign. Do slower streams carry a weaker form of the same process, a different mix, or several histories hidden beneath one name? Before comparing mechanisms, we need to know which kinds of solar wind we're comparing. For a long time, the simplest way to sort the solar wind was by speed. Some streams moved fast, while others moved more slowly, and the slower material went into one broad bucket. That division helped scientists describe what spacecraft were measuring, but it also encouraged a misleading idea that slow wind was basically one kind of solar wind, separated from fast wind mainly by the number on the speedometer. Parker's solar probe made that image harder to defend. As the spacecraft traveled close to the Sun, its instruments measured the plasma and magnetic field passing directly over it. At the same time, near-Sun images provided context for the larger structures around those measurements. Together, those views exposed differences that speed alone had hidden. Material moving at a similar pace could carry different magnetic patterns and different flow signatures. That means the word slow describes an outcome without fully describing the physics behind it. Two streams can arrive in the same broad speed range, even when the plasma inside them behaves differently. It's a little like sorting every person who walks slowly into one group, without asking whether they are climbing a hill, carrying something heavy, or simply taking their time. The measured pace is real, but it doesn't tell you the whole history. The evidence now supports at least two physically distinct kinds of slow solar wind. That is a change in classification, not just a finer measurement of speed. Scientists can no longer treat every slow parcel as a weaker copy of the same basic flow. They have to compare the magnetic behavior, the motion within the plasma, and the surrounding solar structures before deciding what kind of wind they are seeing. There is still no finished map in which every parcel has been assigned a permanent place. Parker's measurements reveal a split, while leaving smaller divisions and uncertain cases unresolved. Some boundaries may blur, and future observations may expose more structure inside each group. For now, the important change is clear. Slow solar wind is an umbrella label covering more than one physical behavior. The question is no longer simply why some solar wind travels slowly. It is which different slow winds have been grouped together under that single name. Parker's close passes have now given those different slow winds names. One is called non-Alfvenic slow wind. The other is Alfvenic slow wind, named for the kind of linked motion that can pass through magnetized plasma. Both can arrive within the broad range called slow solar wind, yet they do not behave as though they share one simple history. The difference appears when Parker measures more than speed. In Alfvenic slow wind, changes in the plasma's motion track, changes in its magnetic field in a recognizable way. The field and the flowing material move together with a stronger connection. In non-Alfvenic slow wind, that relationship is much weaker or takes a different form. A speed reading alone may place both streams in the same box, while their magnetic and flow patterns place them in separate groups. You can think of it as two cars traveling at the same speed after reaching the same road. One came down from a mountain, while the other crossed a crowded city. Their speedometers now agree, but other signs still carry traces of where they have been. In the solar wind, those signs are written into the magnetic field and the motion of the plasma. Parker samples them directly as the wind moves past the spacecraft, while close views of the Sun help researchers connect that passing material with the structures below. This turns the slow wind from a poorly defined middle category into a mixed population. Some of it carries Alfvenic behavior that resembles the better organized patterns once associated mainly with fast wind. Some lacks that pattern and fits the older idea of slow wind more closely. Calling both streams slow remains correct as a statement about speed. It just no longer tells you enough about the physics. The split is a strong reading of Parker's observations, though it isn't a final inventory of every slow stream near the Sun. Some samples may combine features of both classes, others may contain smaller divisions that current measurements cannot yet separate. The names give researchers a better first sort, not a claim that nature has only 2 boxes. Even with that limit, the change is substantial. A slow stream can now be identified partly by how its magnetic field and plasma move together, which means its behavior may preserve clues about the solar region that released it. Those clues point away from a single birthplace for everything called slow wind. Scientists currently connect the non-Alfvenic kind with helmet streamers, the bright arches that rise above the Sun and extend into the corona. The Alfvenic kind is more often linked with neighborhoods around coronal holes where magnetic fields open outward and plasma can escape. A helmet streamer forms around magnetic loops that remain closed near the Sun. Plasma can collect there until a change in the magnetic field releases some of it into space. Near a coronal hole, the field has a more open shape, giving plasma another route out. Each setting can leave different marks on the material it releases. This makes the waves more than a way to sort Parker's measurements. Plasma leaving an open magnetic neighborhood may retain stronger Alfven-like motions, with changes in speed and magnetic field traveling together. Material released around a helmet streamer may have less of that shared movement by the time Parker samples it. If you examine the wind closely enough, its behavior may carry a trace of the magnetic region it passed through. That trace does not give scientists a secure address for every parcel of plasma. Parker measures the wind after it has left the solar surface, so researchers must work backward. Meanwhile, magnetic regions change, expand, reconnect, and lean across the Sun as it turns. By the time we try to link a sample with its source, both the plasma and the magnetic field may have changed along the way. NASA presents these links as the current scientific view, not a completed map. Helmet streamers are strong candidates for much of the non-Alfvenic slow wind, while coronal hole neighborhoods are strong candidates for much of the Alfvenic kind. Neither connection is known to be exclusive, and Parker has not settled where every slow stream begins. The old problem asked where the slow solar wind came from, as though one answer might cover all of it. Parker's measurements suggest a family of smaller problems instead. One class may carry the history of closed magnetic loops and later release. Another may come from open field regions while still moving slowly. The boundaries can blur, and the source assignments may change with better evidence, but the geography now has more than one plausible starting place. That change in language is also a change in the science. Parker didn't simply collect more samples of something already understood as the slow solar wind. Its measurements made the old label less reliable. Once 2 streams show different physical traits, treating them as one kind of wind can hide the clues that might explain how each one formed. Classification can be a major result, even when it sounds modest. If scientists place unlike streams in the same group, every comparison begins with a mixture. One measurement points toward magnetic loops that once held plasma in place. Another points toward open magnetic fields near a coronal hole. Blend those cases together, and the combined pattern may look confused. Separate them, and each stream can be tested against the conditions that could have produced it. Parker has therefore changed the order of the work. Before asking about an origin, scientists first have to identify the class in front of them. Is this the slow wind with strong Alfvenic behavior, carrying waves and magnetic motion together? Or is it the less Alfvenic kind, whose properties fit a different magnetic setting? If you mix them under one name, a disagreement between measurements can look like a failure of the explanation. Once the classes are separated, that disagreement may become evidence that different processes released or accelerated the plasma. The categories aren't finished. Each class may contain smaller groups that Parker's current measurements haven't fully separated. A stream can also pass through changing conditions on its way to the spacecraft, which makes a clean label harder to apply. And while the proposed links to coronal hole neighborhoods and helmet streamers fit the evidence so far, those links remain provisional. They are working assignments that may change as more passes connect local measurements with the Sun below. The gain is still real, One broad mystery has become several testable problems with different measurements and likely birthplaces. Parker hasn't delivered a single answer for the slow wind because the wind itself may not permit one. Scientists can now ask which slow wind they are studying before they argue about where it began. Yet even a better category reaches Parker only after the plasma has crossed the space close to the Sun. If the slow wind is more than one thing, what else in that near-Sun environment can change the signal before Parker measures it? Dust near the Sun can look like background glow, something sitting behind the plasma while the solar wind carries the serious science. Parker showed that the dust was part of the changing environment. As the spacecraft moved closer to the Sun, it measured less light scattered by dust than during more distant passes. The haze was thinning inward. That scattered light gave Parker a way to detect dust without collecting grains one by one. Sunlight strikes the tiny particles and spreads in many directions, producing a faint glow. If there are fewer particles along Parker's view, less light comes back toward its instruments. The decline so carried physical signals. The spacecraft was entering a region where the dust population was being depleted. The Sun is a harsh neighbor for a grain of dust. Closer in, stronger sunlight heats those grains more intensely, while the surrounding solar environment gives them less chance to remain intact. Parker's readings did not have to catch each particle disappearing. The fading glow showed the combined result. Somewhere inward of the spacecraft's earlier passes, dust was becoming harder to keep. Scientists had predicted for years that a dust-free zone should exist close to the Sun. The idea followed from the conditions there, but a prediction does not tell you exactly where such a zone begins or how sharply it forms. Parker added direct evidence that the expected change was happening. Dust did not remain equally abundant all the way inward. Its scattered light fell as the spacecraft approached the Sun, turning a broad expectation into something observations could begin to constrain. This does not mean Parker found a clean edge with dust on one side and none on the other. Its readings support continued depletion closer in and point toward a dust-free region farther down, but they do not yet draw the exact inner boundary. That boundary may also be less like a wall than a region where different grains fail under different conditions. Parker did not move through an empty gap between the Sun and the solar wind. It crossed a dusty medium that changed with distance, and the changing glow became a reading of that medium. The spacecraft made the predicted dust-free zone more than an idea, while leaving its final shape and location unsettled. Dust can sound like a side issue in solar physics. The serious work seems to belong to magnetic fields, charged particles, and the solar wind, while tiny grains provide little more than a faint glow in the background. Yet that glow sits between Parker and some of the structures it is trying to study. It belongs inside the reading story. A spacecraft near the Sun does not observe through a perfectly clear window. Sunlight strikes dust grains and scatters from them, adding a haze around the Sun. If that scattered light fades as Parker moves inward, then the background is changing with distance. A feature seen at one radius is not being viewed through exactly the same surroundings when Parker later sees it closer in. That changes how the readings are understood. Scientists must separate changes in the thing being studied from changes in the material through which it appears. It is a little like watching a distant light while mist thins around you. The light may seem sharper even if the source has not changed, because the path between you and it has. Near the Sun, the physics is far more involved, but the basic caution remains. The viewing conditions are part of the result. Parker was so learning about two connected layers at once. Its instruments could trace structures in the plasma, while the changing dust haze revealed that the surrounding material did not provide a fixed background. What looked clean, isolated, or easy to classify could depend partly on where the spacecraft was and how much dust-scattered light remained along its view. This does not make dust the answer to every uncertain reading. It does not replace the plasma story, determine every signal, or explain every feature that refuses a simple label. The result sets a narrower boundary. Parker showed that the near-Sun environment includes a material haze that changes with radius, and scientists have to account for that change when reading what the spacecraft sees. The tidy drawing of a bright sun, a clear gap, and separate streams of plasma gives way again. Parker is moving through overlapping physical regions, each capable of changing the evidence gathered from the others. Once the background itself is changing, the next task is to look beyond visibility and ask what energy is still being transferred among the particles close to the Sun. Close to the Sun. Energy is still moving through the plasma in ways that older models did not fully allow for. Parker found evidence for one of these processes near the heliospheric current sheet, where magnetic fields pointing in different directions meet across a broad, wavering surface. The current sheet is neither smooth nor still. As magnetic fields break and reconnect, they can form loops called magnetic islands. Some protons become trapped inside them, circling through the changing magnetic field instead of passing straight through. When two islands merge, their fields are compressed and rearranged, and some of that magnetic energy passes into the trapped particles. A proton caught in this process can gain energy as the island around it changes. Parker's readings supported proton energies of roughly 400 kilielectron volts. That unit describes energy rather than speed. But the scale is what we need here. These protons carried far more energy than earlier expectations for this near-Sun structure had predicted. The solar wind was carrying them outward, while something local pushed them harder. That changes the role of the heliospheric current sheet. It is more than a dividing surface between magnetic regions or a feature that guides particles energized somewhere else. Magnetic reconnection within it can build islands, merge them, and turn some of the field's stored energy into particle motion. Parker had encountered an active particle accelerator close to the Sun. Energetic protons are often linked with large solar flares or coronal mass ejections, the obvious violent events that throw material into space. The current sheet process shows that strong acceleration can also happen within smaller structures that are much harder to see from far away. So when you look at the energetic background near the Sun, you're not seeing only the fading remains of explosions elsewhere. Some of that energy can be produced and reshaped locally. The result has a firm limit. Parker supported this pathway and found it could act far more strongly than expected. The probe did not settle how it ranks against every other source of energetic particles. It also did not show that merging magnetic islands drive all major particle events. Parker added a specific piece of working machinery near the Sun, powerful enough that scientists can no longer treat the region as passive background. The dust and the energetic particles may sound like separate discoveries, but Parker found them in the same unsettled place. Once the spacecraft entered the Sun's outer atmosphere, it encountered a medium that changed as the distance from the Sun changed. Even there, between the visible surface and the space beyond, the surroundings were still shaping the readings. The thinning dust made that clear in the most direct way. The faint haze, seen farther out, did not remain fixed as Parker moved inward. It weakened, which meant the spacecraft was passing through a changing field of material, not looking through a permanent background. Parker could measure that change during those close passes inward, because it went close enough for the effect to become clear. What seemed like scenery was part of the physics. Near the heliospheric current sheet, the merging magnetic islands revealed another kind of activity. Magnetic structures could meet, reconnect, and transfer energy into particles with surprising force. Older expectations had allowed for local acceleration, but Parker showed that this pathway could be much stronger than scientists had expected. The space around the Sun was not simply carrying energetic particles produced somewhere else. It could help make them energetic right there. Put those findings beside each other, and the image changes. The near-Sun region is less like a clean laboratory where known effects can finally be measured up close. It is an active environment that alters both what the spacecraft can see and how much energy nearby particles can gain. Parker did more than remove distance from familiar observations. It found interference in the view and physical machinery hidden inside it. There are limits to what those readings settle. The boundary of the dust-free zone has not been fully mapped, so scientists still cannot draw its complete shape around the Sun. The magnetic island pathway also remains one source among several possible sources of particle acceleration. Parker showed that it works, and that it can work powerfully, but not how often it dominates. That leaves us with a sun whose surroundings are still doing physical work before an eruption even begins. Dust disappears unevenly. Magnetic structures rearrange and feed energy into particles. This much hidden activity changed how Parker's closest eruption images had to be read. The events were moving through a region already in motion, not through empty space. A coronal mass ejection seems simple from far away. The sun erupts, a vast cloud races outward, and whatever was thrown free keeps going into space. In that view, the event has one direction. Material leaves, the eruption fades, and the launch site is left behind. Parker Solar Probe's closest images from 2024 and 2025 showed something that didn't fit. After a coronal mass ejection, Parker saw material moving toward the sun. These were inflows, appearing in the wake of an event we usually describe as an outward blast. Some part of the aftermath was coming back. Distance had made that motion harder to recognize. Seen from farther out, the brightest expanding front draws the eye, while smaller movements near the launch region can blur together or disappear behind it. Parker was close enough to separate those local flows from the larger cloud moving away. The eruption had not simply opened a path and emptied itself into space. Magnetic structures near the sun were still changing shape, redirecting material after the main release. That gives us a less tidy image of a coronal mass ejection. Much of its plasma can still travel outward, sometimes reaching planets and spacecraft days later. Yet near the sun, part of the disturbed material may reverse direction as the magnetic field reorganizes. Escape and return can happen within the same aftermath. The region doesn't snap back into place once the bright front has passed. The images do set a boundary on what we can say. They show that some material linked to a coronal mass ejection falls sunward. So a purely one-way model cannot describe every part of the event. They don't tell us how often these inflows occur across all eruptions, or whether they always carry the same amount of material. A close view can reveal a striking process without showing how common it is. Still, the correction is physical, not just visual. Something that had been caught up in the eruption changed course and moved back toward the star. To understand that return, we need to know what Parker was actually seeing, which parts were plasma, which were magnetic structures, and what force bent their motion sunward. What came back was part of the material caught in the eruption, hot plasma threaded by magnetic fields, along with magnetic structures stretched and disturbed as the coronal mass ejection moved away. Parker Solar Probe's close-range images showed some of that eruption-linked material flowing toward the sun again. It hadn't escaped into space with the main outward surge. That change in direction begins with the magnetic field. After a coronal mass ejection tears through the sun's atmosphere, the field lines left behind don't always remain in the shape the eruption gave them. They can break and reconnect in a new arrangement. As they shift, they pull on the charged plasma attached to them. Some of that plasma becomes trapped in the changing field and is drawn back toward the sun. You can think of the field and plasma as moving together, though they aren't tied in a simple mechanical way. The plasma carries electric charge, so its motion responds strongly to the magnetic field around it. When that field rearranges after an eruption, the path available to the plasma rearranges too. A stream that seemed bound for open space can then curve inward and descend toward the region below. That is why the inflow in Parker's pictures is more than a dramatic reversal. It is visible evidence of the eruption's magnetic aftermath taking shape. The returning debris traces the field as it changes, allowing us to see a process that would be much harder to recognize from a distant, flattened view. Part of what the eruption lifted and disturbed is being pulled back into the solar atmosphere. In that limited sense, the sun recycles some of an eruption's remains. Material rises, becomes tangled in the changing magnetic field, and later returns instead of being lost. The evidence does not show that every coronal mass ejection behaves this way, or that a large share of each eruption must come back. It gives us no fixed percentage, and it does not yet tell us how often these inflows appear. What it does show is that an eruption can leave material behind in motion, still being sorted by the sun's magnetic field. Once that returning plasma reaches the atmosphere again, what conditions does it leave there? That returning plasma can change the place it falls into. It carries magnetic material back toward the solar atmosphere, where the field and gas have already been disturbed by the eruption. The region left behind is therefore not simply an emptied launch site. Some of what went out can come back and alter the conditions there. This makes the falling material more than leftover debris. A coronal mass ejection removes plasma and magnetic field from the sun, but the return flow means that removal can have a second phase. Material comes down into an atmosphere that is still adjusting. As it settles into that region, it can change the local structure and the arrangement of the magnetic field. The aftermath becomes part of the physical process. That is important because solar eruptions begin in magnetic environments. If returning material modifies one of those environments, then the region that produced an eruption may not prepare for later activity in quite the same way. The next event would not begin from the untouched conditions that existed before the first one. It would begin in a place partly reshaped by what rose, turned back and returned. Parker's solar probe has therefore changed the simple drawing many of us carry in our heads. An eruption is often shown as one burst leaving the sun and moving into space, with a clean arrow pointing outward. The measurements described by NASA in 2025 add a return path. That path makes some eruptions episodes in a recycling system, where the aftermath can feed back into the atmosphere it came from. This does not mean Parker can yet tell us how strongly the return flow affects a later eruption. The approved finding does not establish how common the process is across the sun, how much material or magnetic field must return before the effect becomes important, or whether the change can improve forecasts. Those limits are still open. What Parker has supplied is the missing causal link. Falling material can modify the launch region itself, so the end of one eruption may help shape the starting conditions for another. We now know that solar debris can return with consequences. We do not yet know how often those consequences change what the sun does next. Parker's closest images are easy to admire. Bright arcs and material moving through a place no spacecraft had seen from that range. Yet their value isn't the drama. Parker was close enough to resolve a process that a flatter, more distant view could make look like a simple outward rush. From farther away, a coronal mass ejection can resemble one release that leaves the sun and continues into space. Parker found motion going the other way as well. Some of the magnetic aftermath can turn back, carrying material toward the solar atmosphere and entering it again. That return changes what we think an eruption leaves behind. The sun isn't merely throwing something away, then waiting unchanged for the next event. Material and magnetic structure can return, meet the atmosphere again, and alter the region from which another eruption may rise. The aftermath becomes part of the next set of starting conditions. Range made this process visible. When several movements overlap along the same distant line of sight, the largest outward burst can hide smaller flows or flatten them into one shape. Parker's close approach separated that activity to reveal an eruption as a continuing process, with material leaving, returning and reshaping conditions at the sun. The images do more than confirm that eruptions are complicated. They challenge the simplest one-way image with evidence of recycling. Once material and magnetic structure can return, scientists must interpret a coronal mass ejection as an event whose effects may continue at its source, even while its most visible cloud is moving away. There is still a clear limit. Parker hasn't turned this inflow into a rule that predicts every eruption. These images don't establish how often the return happens, how strongly it affects the sun, or which later eruptions will carry a trace of it. Strong evidence for one process isn't a complete forecast model. It does show why better forecasts depend on knowing the conditions left behind near the sun. If an eruption rewrites those conditions, then following its outward path gives scientists only part of the account. They also need to know what returned, where it entered, and how the launch region changed afterward. Parker moved closer and made the sun less simple, yet more readable. Its final measure rests not on ending every mystery, but on whether this sharper knowledge can improve forecasts, and on which claims the mission truly settled before its work was done. It's easy to treat Parker's closeness to the sun as the achievement by itself. No spacecraft had gone so deep into the sun's outer atmosphere, and surviving there was remarkable. Yet the distance record wasn't the main practical gain. Parker carried instruments into the region where the corona becomes the young solar wind. There it measured particles, magnetic fields, and energy. Before Parker, scientists could watch much of this region from farther away. They could study sunlight, track features and images, and measure the solar wind after it had traveled outward. Those observations remain important, but they leave gaps. A model still needs a starting state, the local conditions from which an eruption or stream of solar wind begins to develop. If those conditions are uncertain, the forecast carries that uncertainty forward. Parker placed readings inside that difficult starting region. Scientists no longer had to infer every detail from a distant image or from material that arrived later. They gained samples from within the corona, close to the young wind. That gives the physics firmer limits. Models can be tested against the temperatures, particle motions, and magnetic conditions found near the place where the outward flow is still forming. You can think of a weather model on Earth. Even excellent physics will struggle if its starting map has large blank areas. Parker didn't replace the model. It helped fill in part of the map, at a location where the missing signals had been especially costly. The forecast still has to calculate how the system changes after that moment. But its first step can be tied more closely to what the sun was actually doing. This doesn't turn Parker into a forecast button. Better starting conditions can improve a model without instantly producing an earlier or perfectly accurate warning. Measurements must be folded into working models. Those models must run quickly, and their results must become guidance that people can use. Each part has its own limits. So Parker's operational legacy is precise. It brought stronger starting data to a region where space weather models had relied on wider assumptions and weaker remote clues. That is real progress. The physics begins from a clearer view of the corona and young solar wind. Full forecasting skill, though, depends on everything that happens after those readings enter the model. Parker's solar probe touched the sun, but that phrase still needs its boundary. The spacecraft entered the corona, the sun's outer atmosphere. It did not descend to the bright surface we see from Earth, and it did not scrape the photosphere. There was no solid edge waiting below it. Parker crossed into a region defined by the behavior of hot plasma and magnetic fields, gathered readings there, and then continued along its path. That distinction matters because the word touched can make the achievement sound broader than it was. Parker did not turn the sun into a place that spacecraft can approach freely. It reached a carefully chosen part of the solar environment for a limited time, using a machine designed for this single, hostile job. Its success came from respecting severe limits, not from making those limits disappear. In fact, the mission's best results show how narrow our access remains. Parker could sample the corona because its whole plan used brief robot encounters under tight control. The spacecraft could enter the right region, collect data that remote instruments could not obtain in the same way, and carry those readings onward. That is a major scientific capability. It is also a very specific one. We should be careful then about treating Parker as an early rehearsal for people visiting the sun. Human visitation is not what the mission demonstrated, and neither is the ability to linger wherever scientists might prefer. A robotic probe surviving a planned passage does not imply that crews, larger vehicles, or less specialized machines could follow. Even Parker's access was exceptional because the spacecraft and the path were made for each other. So the reach of solar science has expanded, though access itself remains sharply constrained. Parker gave researchers a way to measure the corona from within, which can strengthen the data used to understand the young solar wind and the conditions that shape space weather. That is a powerful result, but also a narrow one. At the same time, its success drew the limit more clearly. We can send a purpose-built machine briefly into the right regime, and bring back better readings, we have not made the sun broadly reachable. Parker crossed a scientific boundary while leaving the physical one firmly in place. Parker's solar probe did not touch the sun's visible surface. It crossed into the corona, the sun's outer atmosphere, and measured that region from within. That correction is simple, but it clears away a misleading image. The milestone was never a spacecraft reaching solid ground or brushing against a glowing shell. There is no surface there to touch in that sense. Parker entered a physical regime that we had previously studied only from outside. That changed the kind of answers solar scientists could build. Before Parker, researchers watched the corona through telescopes, studied sunlight, and measured the solar wind after it had travelled far beyond its birthplace. Those methods revealed a great deal, yet they often required scientists to work backward from distant effects. Parker carried instruments across the boundary and sampled the particles, magnetic fields and waves where the young solar wind was still taking shape. Several old solar mysteries could now be tested against readings gathered in the region that produced them. The strongest results make a short list you can carry away. Direct sampling inside the corona happened. The corona's edge is ragged and changing, not a clean shell fixed at one height above the sun. The young solar wind is structured, with changing flows and magnetic features, rather than a smooth stream spreading evenly into space. These findings are sturdy because they come from repeated encounters under measured conditions, not from one striking image or a single pass. Parker also gave researchers tighter ways to discuss possible mechanisms. An idea about how particles gain energy, or how magnetic structures shape the wind, no longer has to remain a broad possibility detached from place and time. Scientists can ask whether it fits the speeds, fields, particle behavior, and local conditions Parker recorded during a specific encounter. Some disputed mechanisms now have firmer support in certain measured settings, while others face sharper limits. That does not mean every argument about the corona or solar wind is finished. It means the arguments must answer to better evidence. Parker put instruments where the boundary shifts and the wind starts moving outward. Proposed mechanisms could now meet the conditions they claim to explain. The sun is not solved, but several claims that once depended mainly on inference now rest on readings taken in the right place. Uncertainty after Parker is not the same uncertainty scientists had before the mission. It has been pressed into a tighter shape. Direct readings near the sun now rule out some easy explanations and support others under set conditions. Every idea that remains must fit what the instruments found. Knowing more has not removed disagreement. It has made disagreement work harder. One dispute concerns the switchbacks, those sudden bends in the magnetic field. Some may form close to the sun, while others may develop farther out, and the balance between those origins is still being tested. The slow solar wind presents another divided problem. Researchers are still working out which solar regions supply its different forms, and even how those forms should be sorted when their properties overlap. Parker narrowed both debates, though it did not reduce either one to a single cause. The space around the sun also contains dust and fast-moving particles that do more than fill the background. Their sources, motion and effects remain active areas of study, especially where several populations meet. Heating is no simpler. Different pathways may carry more or less of the energy under different magnetic and plasma conditions. The readings can narrow the choices without making one pathway the winner everywhere. Conditions in the corona change across place and time. That leaves solar physics in a stricter position. An idea that sounded plausible from far away can now be checked against one encounter and its measured fields, particles, speeds and location. Some accounts survive that comparison well. Some have lost room to move. Others may fit only a narrower set of conditions than their supporters first expected. The open arguments are so smaller in scope, more physical, and easier to test without pretending that all of them are equally unsettled. This is how Parker changed what it means to say that we understand the sun. It did not solve the corona, the solar wind, the dust, and the heating problem in one stroke. It entered the region where those ideas could be checked, then replaced broad mystery with sharper limits. The result is less satisfying than a final answer and far more valuable to science. We can now separate what Parker established from what it only constrained, and both from what remains in dispute. The sun has become less mysterious in one sense and more demanding in another. Any answer now has to fit the place where the evidence was gathered. Parker's solar probe changed our view of the sun by going where no spacecraft had gone before. It entered the corona and measured that hidden atmosphere from the inside. The mission was built around a simple correction. Touching the sun did not mean reaching its bright surface. It meant crossing into a region where the sun's magnetic field still controls the surrounding plasma, and where the solar wind has not yet fully broken free. From Earth, that boundary once looked smooth enough to draw as a clean line. Parker found something far less settled. The edge of the corona rose and fell around the spacecraft, wrinkled by magnetic structure below. Parker could be inside the corona, then outside it, then inside again. The sun's atmosphere did not end at one fixed height. It shifted as the sun turned and changed. Inside that moving edge, Parker met a young solar wind that was still being shaped. The flow carried sharp magnetic reversals called switchbacks, sudden folds in the field that sometimes turned it back toward the sun. They were not rare disturbances scattered through an otherwise smooth stream. Near the sun, they appeared in groups and helped show that the wind begins with much more structure than older diagrams suggested. That gives scientists better ways to test how the corona is heated and how the wind gains speed. A model now has to match measurements taken where those changes are happening, rather than only matching the wind after it has traveled far from the sun. Parker can compare magnetic fields, moving particles, waves, and energy in the same region. Ideas that once produced similar results at Earth may separate when tested close to their source. The answer is still incomplete. Scientists do not yet agree on the full mix of processes that creates the switchbacks. The slow solar wind may escape through several kinds of magnetic openings, and its exact origins remain under study. Waves, turbulence, reconnection, and escaping particles may all carry part of the heating budget, but their shares are still uncertain. Other measurements remain difficult as well. Particles near the sun can change quickly. Dust behaves differently as it approaches the corona, and eruptions can disturb the region Parker is trying to understand. The spacecraft has watched these effects from remarkably close range, yet it has not observed every possible condition. Even the way eruptions feed energy back into the surrounding corona may vary more often and in more ways than the present record can show. So Parker did not solve the sun as a whole. It did something more exact. It replaced several tidy guesses with direct measurements, found a wrinkled atmospheric boundary, revealed structure in the young solar wind, and gave competing mechanisms a much sharper test. And that returns us to the correction at the beginning. Touching the sun was never about brushing against a solid place. It was about entering an unseen regime where magnetic fields guide hot matter before it escapes into space. Parker crossed into that regime and found that the old clean image was far too simple. The sun is still difficult. Its atmosphere still heats itself by processes we have not fully separated, and its wind still carries traces of events we cannot always follow back to their source. Yet those unknowns are smaller now, shaped by measurements made inside the corona itself. The boundary moves, the field folds, the particles stream outward, and Parker remains there among them, listening to a star before its wind becomes distant and familiar.